Hey guys, this is Mr. Yo, and we're going to talk about Lewis dot structures. So, as you know, you guys actually learned this during class, but if you guys gets confused with it, I want you guys to comment below on this video, or you can ask me during class. So, here we go. First, analyzing the Lewis dot structures. So, covalent bonds generally form when a nonmetal combines with a nonmetal. So what I want you guys to focus is the covalent bond that are formed from nonmetal to another nonmetal. Alright. Both elements in the bond are attracted to the unpaired valence electrons so strongly that neither can take the electron away from the other, unlike the case with ionic bonds. So as we know that covalent bonds are nonmetals and nonmetals, and nonmetals are basically they're sharing the electrons instead of transferring it, because if it's transfer, then it's focusing on the ionic bond. But since we're going over the covalent bond, it's sharing. So the unpaired valence electrons are shared by two atoms forming a covalent bond. Like I said, it's being shared. The shared electrons act like they belong to both atoms in a bond, and they bind the two atoms together into a molecule. So a molecule is basically a combination of elements that are put together. So in this case, two atoms together creates a molecule. Next, the shared electrons are usually represented as two dots or as a line between the bonded atoms. So another one is shared electrons. This is very important in Lewis dot structure because you will encounter a lot while you're actually drawing the structure. So I would say two dots, which is basically something that most of the scientists use, usually students use. So I would recommend two dots instead of the line, because if it's a line, you might have a confusion with the bond itself, and I'll show you as we go on. These represent a single bond. So a single bond, it means in a Lewis structure, a line represents two electrons. So a single bond represents two electrons. So there are three things that we have to know. One is covalent bond, which is nonmetal combining with another nonmetal. Second is that molecule represents two atoms that are combined together. And the third one is shared electrons, which is going to be represented as two dots. Oh, I meant to say four. Sorry about that. So the fourth one, or the last one, is the single bond. A single bond has two electrons. So if we're actually drawing out the structures, the two important point I would say is the two dots being shared electrons, and the single bond. So we're going to move on. First example, NH3. So NH3 contains a nitrogen and three hydrogens. So in this picture, it shows that there are nitrogens. So nitrogen containing 5, so if we look at our periodic table, nitrogen contains 5 valence electrons. So what we're going to do here is I'm going to put N, and I'm going to put parentheses 5 to show that there are 5 valence electrons. Alright, that didn't show well. Next, I'm going to do hydrogen, which is H, containing 1 valence electron. Alright, so nitrogen has 5. If we look at the picture, we only see two dots. The reason why is that the rest of the three single electrons are being paired with the electrons from the other elements. So in this case, the electrons are 1, 2, 3, 4, and 5. So those are your electrons for valence electrons for nitrogen. Next is the hydrogen. So for hydrogens, as we know, it contains 1 electron. So I'm gonna put down this. I'm gonna put a square instead to show that those represent a different electron from a different element. Alright? So there are, like I said from the beginning, single bonds are created by two electrons. So you can see two electrons being combined, which creates a single bond. That's why there's a bond here, and a bond here. These two electrons are represented as shared electrons. In this case, we don't actually touch these bonds or these two electrons because they're shared. And I actually went over through this during class. I said, in a simpler term for you guys to understand it, is represent this bond as a boy, B for boy, and this one as G for girl. So in order to have a relationship, there needs to be a boy and a girl. In this case, this circle could represent either boys or either girls. Okay? So in this case, I'm going to put boy here. Alright? So a boy needs a pair, or it needs to bond to something. In order to create a single bond, it needs a pair of, or it needs another electron to be paired with. So that's why there are the hydrogen's valence electron, which has 1, represents G for girl, G for girl, and another G for girl. That's how it's done. So there are two shared electrons, or one shared electron, and a bond, or 3 bonds in this picture. So I'm going to move on to the next example. So CH4. How many valence electrons are in carbon? So C has 4 electrons, valence electrons, on the periodic table. Next, hydrogen. There are 1 valence electron for each hydrogens. Okay? So I'm going to do the same thing what we have done here by circling the ones for carbon's electron and putting a square on the hydrogen. So there's 1, 2, 3, 4. So there are 4 valence electrons for carbon, and then 1, 1, 1, and another 1. So there are 2 electrons that are going to combine together in order to create a single bond. Alright? So in this case, all the electrons are paired up with the hydrogen's valence electron. Alright, let's go to the third one. H2O. So there's 2 hydrogens and 1 oxygen. So how many valence electrons are there in an oxygen? So oxygen has 6 valence electron. And then hydrogen has 1 valence electron. Alright? So in this case, what we're going to do is circle the 1 for oxygen. Alright? And then put a square on the hydrogen. Okay? So overall, we can see that there are 6, 1, 2, 3, 4, 5, 6 valence electrons with 1 valence electron from each hydrogen. Alright? Okay. So next example. Hydrogen fluoride. So there's 1 hydrogen. Hydrogen has 1 valence electron. And fluoride or fluorine, in this case, there are 7 valence electron. Alright? So since there are 7 valence electron, we're going to count. So 1, 2, 3, 4, 5, 6, and 7. So I'm going to put a circle on here for fluorine. And then a square for hydrogen. Alright? So that's how they created a single bond, or 1 bond, between the fluorine and the hydrogen. Alright, next. CO2. So this, well, for this one, compared to the other compounds, there are double bonds. The reason for that is because if we count this, if you count it out, there's first of all, let's go over the valence electron for each element. So for a C, carbon has 4 valence electron, and oxygen has 6 valence electrons. Alright, so I'm going to actually redraw this so that it can help you guys understand more why there's a double bond and how this actually occurred. So I'm going to draw an oxygen with 1, 2, 3, 4, 5, 6 valence electron. Right? Next, I'm going to draw a carbon with 1, 2, 3, 4 valence electron of carbon. Alright. Next, I'm going to draw an oxygen with 6 valence electron. So the reason why there's a double bond is because, remember, if there is a single electron for each of the sides, up, top, down, left, right, we have to always make sure that each of those lone electrons, or lone boys or lone girls, needs to find a partner. And what we can find out is that there are some electrons that needs to be paired up. So I'm going to pair up these electrons by connecting them with the other electrons. Okay. So I've connected the electrons, and it came out to be like that. So we see a single bond here, another single bond here, which creates a double bond. A single bond here, and another single bond here, creates a double bond. And remember, if there are shared electrons, you leave them as it is. So there are shared electrons that are left over like this, and same goes with the opposite directions. Alright? Alright, last example. HCN has a triple bond and a single bond. Alright? So first of all, we're going to look over, or go over, the amount of the valence electron for each of the elements. So hydrogen has 1 valence electron. Alright? Carbon has 4 valence electron. And nitrogen has 5 valence electron. Alright? Just like CO2, I'm actually going to draw out the structures and let you guys understand it. So, first, nitrogen. So nitrogen, I'm going to put 5 valence electrons. So in this case, I'm going to put a shared electron on the right side and 3 electrons or valence electrons from top, bottom, left side. Alright. Next, carbon. There's going to be 4 valence electrons. And then hydrogen has 1. The reason why I point out the lone electrons toward the central atom is because we are trying to connect the bonds within the central atom and the elements that are right next to the central atom. That's why there is the unpaired, or there is the shared electron on the right side, because we don't want to deal with anything. We just want to leave it as it is. Alright? So I'm going to connect these electrons together because they need a pair. Alright? So now there are one single bond here between carbon and hydrogen, and there are triple bond between CN and carbon and nitrogen. There are 3 bonds here. And also there are 1 shared electron. Alright? So this is the basic understanding of the Lewis dot structure. And next, what we're going to do is we're going to go through the processes of actually drawing out the structure on your own. Alright, so before we actually move on to actually drawing the Lewis dot structure, we're going to solve some problems. So first of all, the first question is, how many covalent bonds do the following atoms tend to form? So there are two possible ways. There's a visualizing way to solve this problem, or you can look at the periodic table to solve this out. So first, for carbon, I'm actually going to draw on a separate sheet of paper. So carbon, C, has 4 valence electrons. Okay. So remember, in order to create a bond, they need to have a single electron that needs a pair with the other elements' single electrons. So in this case, there's going to be 1, 2, 3, and 4. So that means there's going to be 4 covalent bonds. Okay. Another way is that if you look at the periodic table, it should mention here on the periodic table. So you see a C. All right. So remember that this is a first column, second column, third, fourth, fifth, all the way through from the transition middle. This becomes 13, 14, 15, 16, 17, and 18. So there are some cues to this. So in order to solve finding out the amount of covalent bond, what we can do is look at the charge. So carbon has, sometimes it can be positive or negative in this. So in this case, I'm going to use it as positive. So carbon can be 4 plus or 4 minus. All right. The reason why I'm focusing on this 4 is because it's showing that this amount of electron needs to be paired. So in this case, it will be 4 covalent bonds. So these charges represent 4 covalent bonds that can be made through a carbon. All right. And remember this. So if you see 1, then there's going to be 1 plus charge here. If you see a second column, there's going to be 2 plus. For transition metals, these actually determines, because it can be a different charge. This can be a 3 plus or 4 plus, or how many charge it wants to be. So this actually differs, or it actually determines. And then for this one, 13 column. So when you're trying to find the charge for each of these columns, remember to cross out 1. Right? So if you see 13, just cross out the 1, and the remaining would be 3. So this 3 shows that there's going to be 3 plus charge in this column. So I'm going to put 3 plus. All right, same goes with the 14. Cross out the 1, and there's going to be a 4. So this is going to be a 4 plus charge or a 4 minus charge. Okay. All right, and then this one, if you cross out this, there's going to be 5. So we know that nitrogen or any other elements here is going to have 5 valence electron. But remember this, there's an octet rule that you guys must know, or you guys probably have heard or seen it before. Octet rule contains 8 valence electron. Okay, 8 valence electrons. And we sometimes call this full, because in an orbital it would have 8 electrons, and that'll be all. That'll be all filled out. So in this case, since there's 5, we need, or actually, if you remember, if you look at the amount of charge in this side, this would be 3 minus charge, because 8 minus 5 equals 3. So that 3 is going to be the amount of charge for this column. For this one, cross out the 1, there's 6. So there's 6 valence electrons. Alright? But obviously, you guys know that oxygen or sulfur or all these other elements is going to be 2 minus charge. Alright? Same goes with fluorine. Cross out the 1. And there's going to be 7, which is going to be a 7 valence electrons. And 8 minus 7 is 1. So this is going to be 1 minus. For this one, 18. So if you cross out the 1, there's going to be 8 valence electron, which means it will fulfill the octet rule, and there's going to be 0 charge. Alright? So after understanding all these concepts from the periodic table, we're going to go back to the problem. So for carbon, as you know, if it's 4 plus or 4 minus charge, it's going to be 4 covalent bonds. Or if you want to visualize it by putting C and 4 valence electrons around the C and creating a bond for it. Alright? So I'm going to go back to the packet. So this carbon would be 4. Right? Next is nitrogen. So nitrogen has how many valence electron? If we look at the periodic table, there are 5 valence electron. Alright? So I'm going to draw 5 valence electron around the nitrogen. Alright? Next, I'm also going to put, let's see, it's nitrogen, so I'm going to put 3 minus charge here because it's nitrogen. Alright? So what can we actually determine through this? So, like I said, if you have a single electrons surrounding the nitrogen or whichever elements you are determining, you would draw a bond. So it's showing that you can create a bond with these single electrons. And remember, if there is a shared electron, you leave it as it is, because there's a boy and a girl. These couples don't want to separate. They want to be together. Alright? So, this means there's going to be 3 covalent bonds. Alright? And then same goes with here. 3 minus represents 3 charges or 3 electrons that needs to be combined with other elements, electrons. Alright? So there are 3 covalent bonds here. So I'm going to put down 3 here. Next is oxygen. Alright? So for oxygen, I'm going to put an O here. How many valence electrons are there for oxygen? So if we look at back, there's 6 valence electron. Alright? So I'm going to put 1, 2, 3, 4, 5, and 6. So we see 2 shared electrons and 2 single electrons. Alright? So if there's single, they need a couple. So we would create a bond with this, where's 1, and then there's another one. So there's 2 covalent bonds we can create. So I'm going to put 2 covalent bonds. Alright? And also I'm going to put, so it was oxygen, I'm going to put 2 minus. So that means 2 charges, which means there's going to be 2 covalent bonds. Alright? So I'm going to go back to the packet again, write down 2, so we can keep on track. Next is fluorine. So fluorine contains 7 valence electrons. So I'm going to draw 7, 1, 2, 3, 4, 5, 6, and 7. So there are 3 shared electrons and 1 single electron that needs to be paired. So I'm going to put a line here to represent that there's going to be 1 covalent bond created from here. Alright? So, fluorine, if we look at the periodic table, it has a 1 minus charge. So I'm going to put 1 minus, or you can just put F minus. It really depends on whichever you want to decide on. So if we have 1 minus charge or a minus charge, that would create, or that would say that there's going to be 1 covalent bond. Okay, so we have all the, well, not quite. We have one more, hydrogen. Hydrogen, all we know that is that hydrogen has one valence electron, which means there's going to be they're going to have 1 bond created. In this case, H would be plus, or you can write down H1 plus. It really doesn't matter, but there will be 1 covalent bond. Alright, so I'm going to go back to the packet again. and write down 1 here. So we got number 1. Number 2. For number 2, it says, remember from the last unit that atoms bond to have full valence sublevels of electrons. Based on this, provide an explanation for why C, carbon, N, nitrogen, and O, oxygen, and F, fluorine, normally form as many covalent bonds as they do. So I'm going to write down the answer for this problem. So the answer is each of these elements forms the number, I'm just going to put a number sign, alright, of covalent bonds that matches how many valence electrons, I'm going to put E minus because that also represents as electrons, they are missing to get to 8 in its outermost energy level. Okay, so from this point it says each of these elements forms the number of covalent bonds that matches how many valence electrons they are missing to get 8 in its outermost energy level. So if we go back to the periodic table, so the periodic table, usually if you have the other periodic table, it would say 1 or 2, and then 2 and 8, and so forth. So we're going to focus on this 8. Alright, so if we look at the elements CNOF, there's CNOF. Alright, so CNOF is there. So that means they're going to focus on this row, and the most outer sublevel or outermost energy level is 8. Is 8 here. Alright, so in this case, what we have to know, or I'm actually going to draw out each of the elements. So C, N, O, and F. Alright, so I'm going to draw out all the valence electrons. So C has 4, N has 5, O has 6, fluorine has 7. Alright, so it's just saying that they want to try to connect these elements with a covalent bond. So carbon, we already know the information. Carbon has 4 covalent bonds that can be created. Nitrogen has 3. Oxygen has 2. And fluorine has 1. Alright, so this is an important part, but I would say just review this answer and you will get the information. And then next is, why can hydrogen only have 2 valence electrons? So when you see hydrogen, you would say you would kind of question this question, but you will try to you will question it. Why is there 2 valence electrons on this problem? The reason is that it's saying that hydrogen can have 2 valence electrons. We have actually learned that there's 1, but the thing is, the reason for that is that because hydrogen only has the 1s suborbital or sublevel, which means there is no option, sorry about that, for 1p in the first energy level. Therefore, I'm going to put a therefore sign. Its valence level is full with 2 electron or 1 covalent bond. Alright? To specify more, I mean, if you, sorry about that. So if you actually look at the periodic table, like I said on the right side, there's 2 here. Alright? So the reason for that is I'm going to draw this out, the reason why. So hydrogen. Alright? So there's all these different kind of circles all around it. Alright? So, but for hydrogen, there's going to be only 1. So in the first energy level, or a 1s sublevel, alright, there's going to be 2 valence electrons. Alright? We have learned that hydrogen has 1 valence electron. That's correct. But also, there are sometimes, or the maximum amount of valence electron that a hydrogen can have is 2, because we have to bind or bond with this single electron with a different element, or whatever element we want to choose. So I'm going to choose hydrogen because that will be the easiest. So they each have single bonds, and if we connect them, hydrogen has 2 bonds, or 2 electrons. So remember, 1 bond is created by 2 electrons. Alright? So that's why we say that the valence level is full with 2 electron or 1 covalent bond. So this is why we get this. Why hydrogen only have 2 valence electron. Alright? So finally, or now, we're going to learn step-by-step process of how to create a Lewis dot structure. Alright, so drawing Lewis dot structure. These are all these steps, but I'm going to actually not summarize it, but also put it into a term where it's going to be easier for you guys to understand. So the first step, it says to count the number of valence electron for each atom. That's very simple because it's just what it says. So I'm going to put a number sign of valence electron. Alright, so this is a very important step for the first one. So to do so, what we're doing is, for example, there's CO2. So C, there's only 1 carbon, and there's O, which has 2, because it has a subscript of 2. So first, carbon has 4 valence electron, and oxygen has 6. Alright? So we have 4 here, but the thing is, there's going to be a 1 here, saying that there are 1 carbon, and there's 6 valence electron for each oxygen, but the thing is we have CO2, so there's 2 oxygen, so we're going to put a 2 here. So 6 times 2 is 12. Alright, and then 12 plus 4 is 16, so we have an overall of 16 valence electron on CO2. Alright, next step. The center atom is usually furthest left on the periodic table. The exception to this is hydrogen, which can never be in the center. The reason why hydrogen can't be in the center is because hydrogen has 1 valence electron. Alright? And also, if we look back at our notes, remember that hydrogen has a first S sublevel, or their maximum amount of valence electron is 2 electron, or 1 covalent bond. So that's why hydrogen can't be never in the center. Alright? Place the center atoms in the middle and the other atoms surrounding it. Okay, so now if we go back to the example, there's CO2. So we put C in the middle. Why? Because if we look back, CO2, this C represents, or most of the time, or overall, most of the time, whatever elements in the front usually becomes the center atom. So in this case, C is all the way in the left side on the compound, so there's going to be C in the middle as a central atom, and O surrounding the carbon. All right. Next, connect all atoms to the center atom using a single bond. So we're going to have a line that connects with C and the O here, number 1 O, and then number 2 O connecting with the central atom. All right. And then the next step is subtract 2 electrons for every single bond you drew. So what it's saying is that subtract the amount of valence electron that has been used up. So we have a total of 16, total valence electron, which is 16, and then minus the 2 times the number of number of lines. So remember, a line contains 2 electrons. So that's why there's a 2 here, and then there's the amount of lines for that. So we have 1 and 2 single bonds. So we're going to put 2 here. So that's why there's a 2 here, and 2 times 2 equals 4. 16 minus 4 equals 12. So we have 12 valence electrons left over to be drawn on this picture or on this structure. All right. Next, it says fill the octet of the outer atoms by placing electrons as a dot on each outer atom until they have 8 valence electrons. Remember that each line counts as 2 electrons. In the example to the right, each oxygen would need 6 more electrons to have 8 valence electron. Okay, so the only thing that you have to focus is to fill the octet, all right, of the outer atoms. So what it's saying is that you need to fill out the octet on the outside, not the central atom, but the outer area. So it'll be this O and this O, all right? So if we remember, oxygen has 6 valence electron. And if you look at it, you guys might say, oh, how come there's only 7 valence electron? But remember this, the reason why it fulfills the 8 octet rule, or the octet rule, is because there's 1, 2, 3, 4, 5, 6, 7, but also remember, if you're bonded to something, that will be counted as the electrons for this side, for the oxygen. So there's another electron here combined from the carbon. So that's why there's 1, 2, 3, 4, 5, 6, 7, and 8 electrons, valence electron. All right, I'm going to put just an electron here. It's valence electron, but I'm going to put electron here. And the same goes with here. It's going to be 8 valence electrons. All right. Next, what we're going to do is we're going to subtract. We're going to subtract the amount of electrons used up. So there's 12 leftovers that we had from back all the way here. You're going to subtract that with the amount of dots we used. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So we're going to do 12 minus 12 equals 0. So this 0 represents a charge. So if we go to the next step, it says if there are any remaining elements, place them as dots on the central atom. You cannot place more electrons than you have left in your current electron count. So it's basically saying, it's asking for how much charge you have or how much valence electrons are left over. So in this case, it's 0, which means there's going to be 0 charge. That means there are no electrons are left to place, which means no change, which means this is it. All right. So this is all the valence electrons used up. But lastly, there's something that we have to go over in the next step. So if we go back, or if we go to the next step, it says, once you have run of electrons, check to make sure the central atom has 8 valence electron. If not, the electron must be moved as pairs from the outer atoms to be shared between central atoms and the atoms from which the electrons were moved. Continue doing this until the central atoms has 8 valence electron. All right. So basically, what you have to know is that central atoms has to have 8 valence electron. It has to fulfill the octet rule. So if we ignore all these arrows going over, if we count the amount of valence electrons within the carbon right now, there are 1, 2, 3, 4. So there are 4 valence electron. All right. So we can't just randomly add electrons into carbon in order to fulfill the octet. So what we're going to do is we're going to move this pair, all right, all the way here. So it's going to create a double bond here. Same goes with the right side. We're going to take a shared electron and create a bond with it, which gives you a double bond. So if we count out the amount of electrons used, or that is around the central atom, there are 1, 2, 3, 4, 5, 6, and 7 and 8. So there are a total of 8 valence electron here now. So that means it fulfilled the octet rules on the central atom, on the outer atoms, and overall there are a total of, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There is a total of 16 valence electrons with 8 valence electron for the central atom and the outer atom. So this overall is your final product. Alright? Since we went over this process, step-by-step processes, we're going to actually go over some example problems and some problems that will help you out in order to work on these compounds on your own. Alright? But for now, I'm going to actually go over every single one of the compounds that are provided in this packet so you guys could understand it. So first, nitrogen and trifluoride, so NF3. There are 1 nitrogen, so we have 1 here, and there's 5 valence electron for nitrogen. So that's why there's 5 times 1 equals 5. Alright? Fluorine there's 3 fluorines times 7 valence electrons, which would give you 21. And the overall valence electron would be 5 plus 21 gives you 26. So this is the overall valence electron. Alright? And then the next step is that we are supposed to draw out the overall, or we have to find out which one's the central atom. So like I said, whichever is on the left side of the compound would be your central atom, right? Or with the one that has the fewest. So N, nitrogen, would be your middle. There's going to be F surrounding it. Alright? Next step was to draw a single bond or a bond that are connected to each of these elements. So NF, NF, and NF. So we have 1, 2, 3, 4, 5, 6 valence electron used. So from the overall 26, we have subtract by 6 here, which would give you 20 valence electron left over. And then what do we do next? Well, through the step, it says that the outer elements needs to be fulfill the octet rule. So what we're going to do is we're going to put down the rest out. So fluorine has 7 valence electron. So like I said, 1, 2, 3, 4, 5, 6, 7, 8. So that fulfills the octet. Same goes with the other fluorines. Alright. So there it gives you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there's 18 electrons used up. So if we have 20 left over, subtract the 18, that would give you 2 valence electron left over. But wait, didn't we have 0 charge when we did CO2? That means that there's going to be no charge or nothing being changed. But in this case, there are 2 here. Why is that? Is because nitrogen, remember, nitrogen has 5 valence electron, but we have 1, 2, 3 here. So what do we do with this 2 electrons left over? Well, first thing is that we have to put to a shared electron, which will give out the rest of the 2 here. So if we subtract that by 2 again, that will give you 0. So there's 2 here on the top. The reason why I put it here, it can't be on here, because if you put that on here, that means there's a bond being created again. So you're going to put a bond here, which does not fulfill the octet, because there will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There will be 10 valence electron. That does not make any sense. So that's why we're going to put over here. Or we can put it on the corner side, on the diagonal side here, or here. It really depends, but this would be the the best choice for the Lewis dot structure. Alright, so there's that. Next is H2S. H2, so there's hydrogen, which gives, there's one valence electron and 2 hydrogens. And we're going to multiply that. That gives you 2. S or sulfur has, 6 valence electron, and there's only 1 here, so that gives you 6. And if you find the overall of it, 2 plus 6 gives you 8. Alright, so now what we're going to do is same process. We're going to have S and H surrounding it. Alright, so we're going to put overall 8 valence electron and create a bond between those two central atom and the outer atoms, which would have 1, 2, 3, 4. 4 valence electron used. Subtract that by 4, gives you 4 left over. So now what do we do with this leftovers? Well, first of all, we can't use these 4s and just put it in the hydrogen, because remember that hydrogen has a maximum of 2 valence electrons. Alright? So that's why we're not going to put any charge on the hydrogen, but we're going to put those charge onto the sulfur. So sulfur, since there's going to be 4, remember that each shared electrons have 2 in them. So we're going to put 2 here and 2 here. And then you're going to ask, Mr. Yo, is there any other way that you can actually draw this structure? There is. One is sulfur here, and H, gonna bond, and 1, 2, 3, 4. So you can actually structure it like this too. Either way is fine. Well, they're both good structures, so you can use either one of them and it'll be fine. Alright, next is F2. Now you guys will be asking, so there's only 2 fluorines, or there's only 2 Fs, so what do I do? Well, it's not that hard. It's just fluorine has a valence electron of 7, and you're going to multiply it by 2, because there's 2 fluorines, and that will give you 14. So in this case, we're going to put 2 fluorines, alright, and a bond. So 14 minus 2, because there are 2 electrons within a bond, gives you 12. So what do we do with this 12? Well, what we do is we put these 12s valence electrons on the fluorines. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Alright, so there is your final structure for difluorine, or F2. Alright, now we're going to move on to the next problems. Alright, so next is OF2. So OF2, there are 1 oxygen, so I'm going to put O equals, well, there is a total of 6 valence electron for oxygen and 1 here, which will give you overall of 6 valence electron. And F2, there's F equals, there are 7 valence electron times 2, because there are 2 fluorines in there, which will give you 14. Alright, and then 6 plus 14 gives you 20 overall. Alright, so next would be that we have to use the central atom first in the middle, connecting with 2 fluorines next to each other. Alright, next we have to put a single bond that connects with oxygen and fluorine, which would, what we would do is we have overall 20, and there are 1, 2, 3, 4 valence electron used up, which would give you 16 valence electron not used yet. Alright, and then next step is to fulfill the octet rule by getting the valence electrons around the outer elements. Okay, so there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 electrons used up. Alright, so from the 16 we're going to subtract the 12, which gives you 4. So this 4 valence electron, so there are four valence electrons left over. So what are we going to do with this 4? What we're going to do is we are going to plug it in to the oxygen, because these both sides are actually completely done because they follow the octet rule. So we're going to have 4 valence electron, so we're going to put 1 here and then 1 on the bottom. Alright, so this is the structure of OF2, but there's also another way you can put it, but I mean, it's basically the same thing as if we go back. We had for H2S or H2S that it shows a bent structure. You'll probably learn the structure naming later, but there's this structure and there's this structure. Same goes with this one. You can make an L shape out of it, or something else, whichever you like. It really doesn't matter, but there's your structure. Alright? Alright, so for the rest, I mean, you probably understand how to do it, so I'm going to probably show you some shortcut, or my way of doing the shortcut. Alright? So first of all, well, I'm going to mark all these amount of valence electron first, because you'll probably need to fill these out. So I'm going to do this quickly. So carbon has 4 valence electrons, and there's only 1, so that's 4. H has 1, and there's only 1. Cl has, Cl has 7 valence electron with 3, so there's 21. So 4 plus 1 is 22, 26. Okay. Si has, how many valence electrons are there? Si, let's see, how much valence electron does Si have? Okay, Si has 4. So Si has 4, and there's only one Si, so there's 4. O, there's 2 O's with 6 valence electron. Alright, it sounds like I'm talking to myself, but just bear with me. So there's 16 in total. And C, there's 4 valence electron, and there's 1, which means there's 4. H, there are 1 and 2. There's 2 hydrogens and 1 valence electron in each. And then O has 6 valence electron, and there's only 1. So that will give you 4 plus 2 plus 6 gives you 12. P has 5 valence electron, so 5, and there's only 1 there, so 5. Cl3 has 7 valence electron with 3 chlorine, so that will give you 21. 21 plus 5 equals 26. And O has 6 valence electron with 2, so that gives you 12 overall. N has 5 valence electron times 2, because there's 2 nitrogen, gives you 10. Alright, so we got all these valence electrons figured out in this section. But a shortcut to do this is this. So first of all, we know that carbon has 4 valence electron, and this would be the central atom because it's on the left side. So we're going to put C and put each of the valence electrons, or 4 valence electrons in each side. Alright? And next, what we're going to do is we're going to put hydrogen, and then chlorine, chlorine, and chlorine. Remember, and then what we're going to do is put the valence electrons on each of the elements. Alright? So chlorine has 7, so I'm going to draw 7. 1, 1, 2, 1, 2, 1, 2, 1, 1, 2, 1, 2, 1. Okay, so now what we have to focus on are these single electrons that does not have a couple. So H has 1 here, and then C has 1 there, so we're going to connect those 2 together. There's 1 here, connect them, connect these, connect these. Alright, so this is actually the overall structure for CHCl3, but this is an easier way to draw it, but I actually don't recommend as much of it, but it's an easier way to solve the structure and it saves more time. But this is when you're actually getting used to how to actually draw the structures at all. And also, these are very important. I wouldn't ignore it, because in order to find accuracy within the structure, we need to know the amount of valence electron in total and all. So I don't highly recommend this, but I do kind of recommend it because it saves you time and it's better that way. And also, but the thing is, if you're taking it on the exam, remember to do the step-by-step process of putting the valence electron and finding out the exact amount of electrons that are in the outer atoms and also the central atom. Alright? So if we go through the step-by-step process, there's 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 valence electrons for the central atom. Chlorine has 1, 2, 3, 4, 5, 6, 7, 8. So there's 8, 8, 8. And then remember that hydrogen has the most valence electron that a hydrogen can have is 2. So there's 2. So this is the actual structure that needs to be drawn for this compound, right? So for SiO2, so simpler way to do this is Si, there are 4 valence electrons, so I'm going to put 4 valence electrons. And then there's 2 O's, so I'm going to put O here and an O here. Oxygen has 6 valence electron. Okay. Next, I'm going to connect those electrons that are by itself. So connect, 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 connect. Alright, so they're all connected. So if we actually put this into a visualization of the Lewis dot structure, there's going to be this shown. So this is the actual compound or actual structure that needs to be drawn. Alright, so on the exam, I want you guys to draw it like this. Not like this, because this is kind of not professional, unprofessional, but we want to make it professional and more visualizable for it to be graded. Alright, so put it in this way. So CH2O. Alright, so remember, whenever the elements on all the way on the left side, it would be the central atom. So carbon has 1, 2, 3, 4 valence electron, and then there's two H's, so I'm going to put just random H here, and then oxygen here. So remember, hydrogen has 1 valence electron in each, and oxygen has 6 valence electron. Alright? So we're going to connect those lone electrons together. Alright? And there's going to be connection here, and then connection here. So this is kind of unprofessional, so we're going to put it in a professional way. So we're going to do is we're going to put an O on the top and put the valence electrons, double bond with C, hydrogen, and a hydrogen. This is a professional way to draw it, or you can put this sideways and make it a cross symbol, putting it left, right, and then top, bottom, because that will be easier for you guys to understand it, but you can actually draw it like this too. Alright, so next is PCl3. P, how many valence electrons there? 5. So 1, 2, 3, 4, 5. Chlorine, there's 3 chlorines, so I'm going to put Cl here, and then Cl here. And remember, chlorine, there are 7 valence electrons, so I'm going to put 7 here, 7 here, and then 7 here. Alright, and then the lone electrons would be connected together, which would give you this structure. Just to make sure, let's check the octet rule for the central atom. There's 1, 2, 3, 4, 5, 6, 7, 8. So it fulfills the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electron in each for the outer atoms. Perfect. This is a perfect structure. 2 more to go. So oxygen. There's going to be 2 oxygens. Alright? And we're going to have 6 valence electron for each. Alright, so lone electrons, we combine them together. Alright, and also in this structure, the reason why you leave it as in this format is that because these shared electrons won't connect with these shared electrons because they're already shared. We don't want to separate these couples together. And this structure would become like this. So this is a professional way, this is unprofessional or unprofessional. So this is the right answer. Alright? And then lastly, N. N has 5 valence electrons, so I'm going to put 5 on here, 5 on here, and then connect the electrons, which will give you a triple bonds. Alright, so this is the professional way. So I'm going to actually give you a simple explanation why you can't have a double or a shared electron connect with the other electrons, single electrons. It's very simple. If you think of it this way, then you'll probably be surprised in some ways. Let's say O, and then O here. Right? So I'm gonna put the shared electrons inner side or inner area instead of the outer area. Reason is this. This is very simple. Think of this as boy and a boy, boy girl, boy girl. Same goes with here, boy girl. I'm gonna put girl here and then boy here, and then boy and then boy. All right. So these are singles, so they need someone to be connected with. But the thing is, we can't connect like this. This is not possible. The reason why is very simple. If you think of it this way, you will never ever combine these bonds ever again when you're drawing the structure. Simple is, this is a girl, this is a boy and a girl and a boy. So they're already couples, but the thing is, we don't want these couples to cheat on each other, because if this boy goes with this boy's girlfriend and this girl goes with this girl's boyfriend, that's completely cheating. We don't want this cheating going on. Alright? We want these couples to be nice and just having a healthy relationship. So that's why we don't want this to occur. Alright? So we want these boys, and actually since these are boys, I'll put girls here. Alright? Since there are boys here and then there's girls here, we want them to be paired up, not them. Alright? Simple as that. Okay, so the next side, there's going to be a short note, and that'll be the final for the structure, Lewis dot structure, and there's going to be a practice problems, and we're going to actually go over that. Alright. Alright guys, so this is the last part of the Lewis dot structure notes, and so let's get it. Alright, so exceptions to the octet rule. Let's see. Carbon, nitrogen, oxygen, and fluorine bonds have 8 valence electrons, as you saw in the model 1. Because these elements are so common and abundant, this has become known as octet rule. However, it is only a rule for that small list of elements. Alright, so we know that octet rule means that there needs to be 8 valence electron. Let's remember that. So hydrogen, as we know, as we saw, will only ever have a duet, or 2 electrons, because its first and only energy level can only hold 2 electrons. So we already know this, that hydrogen can only have 2 valence electrons, which is actually shown in the previous pages. And then beryllium and boron are other notable exceptions that will have fewer than 8 valence electrons after bonding. Barium has will only have 4. Its 2 valence electrons can make 2 covalent bonds. Alright? And boron will most commonly have 6 or 3 valence, making 3 bonds. So boron is a 3+ charge, and beryllium, I believe it's, how many charges is beryllium? So beryllium has 2+ charge. Beryllium is Be. I'm going to put Be here, 2+, and then boron has 3+. Alright, so you can remember that. So this is basically saying exception. Alright, so exception is saying that you don't actually have not need 8 valence electron. So I put not need 8 valence electron. this is a special case saying that it doesn't actually have to fulfill the octet rule. Okay, next. Almost all other nonmetals not mentioned have the ability to hold 8 or more valence electrons, starting in the third period. Nonmetals have d sublevels available in the third energy level to put more electrons than just the SNP sublevels of the second energy level, which can only hold 8. Thus, elements like sulfur, phosphorus, chlorine, bromine, iodine, and etc. can all form molecules that bond to more than 4 atoms, or have more than just 8 electrons around them in the Lewis dot structure. Okay, so basically saying this is when it's fewer than 8 electron. This part is saying more than 8 valence electron. All right, so when they mention about the d, where is it? So more valence electrons. So d orbital, d sublevels. Where is it? So there's d sublevels. If you look at your periodic table, what they're saying is that this side, these two columns, they are called the s orbital. I'm not sure if you guys learned this, but this represents the s orbital. All the way here, these gases, or from group 13 to group 18, are called the p orbital. Sorry about the spelling. And then the transition metal are called the d orbital. Alright? Like I said, I'm not sure if you guys learned this before, but this is how it is in the periodic table to remember it. Okay? So s orbital is the group 1 and group 2. D orbital is from group 3 to group 12. And from group 13 to 18 is the p orbital. Alright? Just remember that. And it's saying that there is a possibility of having more than 8 valence electron used. Alright? So, let's go on to the problems. Alright. I'm going to skip the valence electrons method, the step-by-step process, because it takes too long, so I'm going to go through the actual Lewis dot structures. So boron, how many valence electrons are there? There's 3. 1, 2, 3. So hydrogen, there's 3 hydrogens, and how many valence electrons are there? There's 1 in each. Alright, if you combine them together, that will create a bond in each. Alright, so in this case, there are fewer than 8 valence electrons, because 1, 2, 3, 4, 5, 6. There's 6 valence electrons surrounding boron. Alright, so this is an exceptional case, and also this is the right Lewis dot structures to be drawn with. So I'm going to just put the, just in case, I'm going to put the number of valence electron overall. So boron has 3, and then there's 1 of them, which gives 3. Hydrogen, there's 1 valence electron for each hydrogen, and there's 3 hydrogens in total. So that gives you 3 plus 3 gives you 6. Just to make sure, 1, 2, 3, 4, 5, 6. 6 overall valence electron. There you go. And then barium chloride. Alright, so the Be has, we found out that there are 2 valence electron, and there's only 1 of them, so that's 2. Chlorine has 7 valence electron with 2 of them, so there's 14. So 14 plus 2 gives you 16 overall. Alright, so barium, Be. So I'm going to put 2 valence electron, and then chlorine right next to it. Alright, and then I'm going to put the rest of the valence electrons for the chlorine, which has 7. 1, 2, 3, 4, 5, 6, 7. Okay, so each of the lone electron are paired up, so it gives you this structure. Barium, there's 1, 2, 3, 4. So there's only 4 valence electron for barium, and it does not fulfill the octet rule, but this is an exception. So that means this structure is right. And let's go over if it's right or not. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 overall electrons used. So this is the right electron, or right structure. Okay, 2 more to go. So boron has how many valence electron? There's 3. There's 1 of them, so that gives you 3. Chlorine has 7, and there are 3 chlorines, so there are 21. So 21 plus 3 gives you 24. Alright? And then that means, let's see, so boron has 3 valence electron, and chlorine has 7. So I'm going to put all the chlorines, put all the valence electrons for each of the chlorines. Alright. Alright, and then remember, the single electrons needs to be paired up. So there's the bond. So are there 24 overall structure? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. So this means this structure is right. Alright? Let's see. And then there's beryllium hydride, or BeH2. I might have named it wrong, but let's go. Alright, so beryllium has Be, so Be has 2, and there's only 1 of them, so that gives you 2. Hydrogen, there are 1 valence electron in each, and there are 2 hydrogens there. So that gives you 2 plus 2, gives you 4. So there are 4 overall four overall valence electrons. So we're going to draw it. So beryllium, there are 2 valence electron, and then let's put hydrogen next to beryllium, so 1 in each. Combine the lone electrons, and there you have it. 4 valence electron, 1, 2, 3, 4. There's your 4 overall electron. Alright, perfect. So this is showing the exception of saying you don't have to actually get an octet. You don't have to follow the octet rule with these exceptions when there are fewer or more electrons, or fewer or more valence electrons within the central atom. Alright. Now we are going to have some practice problems, and I will help you guys solve that out together. Alright guys, so now that we actually learned all the Lewis dot structures step-by-step process, and like the terms that we need to know and how to solve it out. So now what we're going to do is the Lewis dot structure, or Lewis structure part 1, the practice problem. So all these notes that are written on here, these notes are all in your previous notes or previous pages that we just went over, a few minutes ago. So I'm going to ignore all these, and all this. This is a step-by-step process of how to create a Lewis dot structure. So now there are 20 questions that we have to draw Lewis dot structures. So what I'm going to do is I'm going to draw you the structures and explain it to you how these structures relate with the compound itself. So I've written all these problems on a separate sheet of paper, so I'm going to show it to you step by step. So first is NF3. So we know that N is a central atom because it's all the way in the left side, and it has less amount compared to fluorine. So I'm going to put N here, and there are 5 valence electrons. Alright, and then I'm going to put fluorines around the nitrogen, and there are 6 valence electron, or sorry about that, 7 valence electrons for each fluorine. Alright, so now what I'm going to do is I'm going to pair up with the lone electrons, and that will create bond. Alright, and overall, let's see if it fulfills the octet rule. So there's 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electron for the central atom, and 1, 2, 3, 4, 5, 6, 7, 8. There's 8 electron for the outer atoms, and that would be the same as the others. So this is the right structure. Alright, so I'm going to put a square on it. So this is the right structure. Next is H2S. S has 6 valence electron. Alright, and H has 1 valence electron. Remember, for H, the maximum amount of valence electron it can have is 2. So we're going to connect these single electrons together, and let's see if it fulfills the octet rule now. So S has 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electrons. Hydrogen has 1, 2, 1, 2. Perfect. So this fulfills the Lewis dot structure. Alright, and F2. F2 has, so there's 2 fluorine with 7 valence electron for each atom. Alright, so we are connecting the lone electrons together, and let's see if it fulfills the octet rule again. So 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 valence electron here and 8 valence electron here. So that means this structure is right. And remember, if I'm going too fast on this, remember to pause the video and be able to go over it through on your own and make sure you got this all correct. And also, if you guys have questions, remember, ask me during class, or what you can do is just write some comments on this video and I'll answer those questions for you. Alright, so next is CO. So CO, let's write CO first. So C has 4 valence electron and O has 6 valence electron. Alright, so let's get the lone electrons together first. So there's one and then there's another. Alright, so CO. So remember this, we have to fulfill the octet rule. So there's 1, 2, 3, 4, 5, 6 valence electrons on here. And there are 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electron here. But the thing is, if we want this to fulfill the octet rule, what we can do is we can bring this pair and create a bond. So bring it here and create another bond. So if we were to redraw it, there's a paired electron here. Oxygen, there's going to be a triple bond. So there's 2 bonds here, and then another bond from the paired electron that became a bond. And then we're going to draw the leftover. So this would be the right structure. Alright. Next, SO2. So for SO2, there's 6 valence electron for sulfur. And then there's 6 valence electron for oxygen. Okay, so we're going to connect the lone electrons together. So I'm going to connect them together. Alright, and then we have leftover of electrons. In this case, what we're going to do is we are going to, unfortunately, we have to separate these couples into different locations. So what we're going to do is we're going to create a bond by connecting those together. So if we were supposed to redraw that, it will come out to be like this. So remember, guys, remember the exception that we had for some of the elements. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 valence electrons. So this is an exception of having more valence electron than it originally had. So if we go over to oxygen, there's 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 valence electron here and 8 here. So this is an exception. You guys might get a little bit confused with it, but if you keep on practicing it, you'll understand why. Alright, so oxygen. Oxygen, there are 2 oxygens, right? 2 oxygens, and there are 6 valence electron in each. Alright, so I'm going to pair up the lone electrons together. So that will give you this structure. Alright, so if you got that, then you got it right. Okay, next we're going to SF2. Alright, so sulfur has 6 valence electrons, fluoride has 7 valence electron. Okay, so I'm going to pair up with the lone, oh, I forgot the 2 electrons there. So I'm going to pair up with the lone electrons together, and that would be your structure. So there's 1, 2, 3, 4, 5, 6, 7, 8. 8 here, 1, 2, 3, 4, 5, 6, 7, 8. 8 here, and 8 here. So that means it fulfills the octet rule, and we are done with this problem. That's how it is. And then boron. We saw this from the previous page. So boron has 6 valence electrons. I mean, not 6, 3 valence electrons. And hydrogen has 1 valence electron in each. All right. So now what we're doing is we're going to connect the lone electrons together, and that would be it. So in this case, it's an exception of 1, 2, 3, 4, 5, 6. 6 valence electron around boron. So this is an exception, but this is the right way to draw the structure. All right. Next, CHCl3. So C is in the central atom because it's in the left side. So I'm going to draw a C here. All right. H and Cl be surrounding it. All right. And remember to draw the valence electrons. There's 7 in chlorine, 7. And then 1 for hydrogen. So I'm going to connect those lone electrons together. And voila, there are your structures. So carbon has 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electron here. Chlorine, 1, 2, 3, 4, 5, 6, 7, 8. 8 here. 8 here, 8 here. This has 2 because hydrogen has the lowest, or has the most of 2 valence electrons. So this is the right structure. Okay. Now the next problem is CS2. For CS2, there's going to be 4 valence electrons for C, and then S has the valence electron of 6. Okay. All right. So what we're going to do is we're going to connect the lone electrons. Alright, so this comes out to be a double bond and another double bond. So let's count 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electron in the central atom. 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electron in the outer atom. Same goes with here. So that means this is the right structure. Alright, so this would be the first 10 problems of the practice problems. So if you got them right, then good job. So we're going to move on to the next problem. So this is number 11 now. So number 11, BeCl2. Be has a valence electron of 2, and Cl has 7. All right. This is probably from the previous page too, but you probably know what the answer is. So just gonna draw it out. So this is your structure. Beryllium has 4 valence electrons, so 1, 2, 3, 4. Perfect. So this fulfills the octet rule. All right. Next is hydrogen cyanide, or HCN. All right. So first, C would be the central atom because H cannot be the central atom due to having 2 as their most valence electron. Alright, so I'm going to put C in the middle with 4 valence electrons around it. And then I'm going to put an H here and nitrogen on the right side, which has 5 valence electron. Now what I'm going to do is I'm going to connect those lone electrons. So there's going to be H with single bond with the central atom and a triple bond with the nitrogen with the central atom. So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electron in the central atom. 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electron on the outer atom, and for hydrogen there's 2. So this is the right structure. Alright, next is C2H2. For this one, there's going to be 4, or in this case, we probably didn't went over this in our notes. It's not on our notes, but there are in this case, we're going to put 2 C's right next to each other. We're going to count both of them as central atom. But first, I'm going to put 4 valence electron, all right, around. And in this case, for the hydrogen, I'm gonna put it in the outer area. So count this as 1, and I'm gonna put it on the side-to-side area. All right, and hydrogen has 1 valence electron. Next, what I'm gonna do is I'm gonna connect those lone electrons. So 1 and 1, 1, 1. Next is I'm gonna connect these together, which would give you H with single bond with hydrogen, triple bond with 2 carbons, and a single bond for hydrogen. So that will be your structure. Let's go over it if it's right. So 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 here. 1, 2, 3, 4, 5, 6, 7, 8. 8 here. And then there's 2 valence electron for the hydrogen. So that would be your structure. Okay. Whew. Now next is SiO2. So Si, silicon, has how many charges there? Let's see, silicon has, how many charges are there in silicon? Silicon has 2 valence electrons. Is there 2? Give me a sec. Let me look at the periodic table. Oh, there's 1, 2, 3. There's 4 valence electrons. Sorry about that. 4 valence electrons. All right. I'm going to put O next to it, and there's going to be 6 there. I'm going to connect the lone electrons. Oops. All right. So that will give you a double bond on the silicon with oxygen, and same goes with here. And let's see the octet rule. Fits 1, 2, 3, 4, 5, 6, 7, 8. 8 in the middle. 1, 2, 3, 4, 5, 6, 7, 8. 8 here, and then 8 here. So that means this is going to be your structure. Alright, next is H2O2. Okay, so now we are going to use oxygen as the central atom because oxygen has the more valence electron compared to hydrogen, which only takes 2 valence electrons. So I'm going to put O here, and then a O here again. Alright. And then next, let's see. Next, I'm going to put hydrogen next to each other. Alright. So oxygen has 6 valence electron. Hydrogen has 1. Alright. Connect those lone pairs, lone electrons. Okay. Now let's check if it's right or not. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And there's 2, and there's 2. So the answer for this would be this itself. Okay. So we got it down. And let's see. SO4 minus. So for SO4 minus, there's going to be an S in the middle. 1, 2, 3, 4, 5, 6. And I'm going to draw 4 O's. So there's 1 here, 1 here, 1 here, 1 here. This is something that you guys didn't learn this about because it's not on the previous page of the note. But if you want to learn this, feel free to listen to it or skip this part if you guys want to. So there are, oops, drew it wrong. So there are 6 valence electrons in an oxygen. Okay, so this is what I'm going to do. First, I'm going to connect each of the bonds. So I'm going to put 1 here, 1 here, 1 here. I know we're not allowed to take the pairs, but in this case we could because it's an exception. And 1 here. And now we have 1, 2 left over here, and 1, 2, 3, 4 left over. So in this case, there's a 2 minus charge here. If it says 2 minus charge, that means you're putting in 2 extra electrons in it. So we are going to put randomly here, and then here. Alright, so that means there's going to be 8 valence electron overall here, 2, and then to solve this out, what we can do is we can draw, let's see, draw this electron being connected to this one right here. Alright, and then this one connects with this one. So if I redraw it out, there's going to be a single bond with oxygen like this. Same goes with another one. Okay, double bond O on this one, and another double bond here. Alright, in actuality, or in reality, this is not actually the right way of drawing it out, or it might be a right way to draw it out, but it's not actually, well, recommended as much. But in this case, since we have all these octet rules being solved out, remember that there needs to be a bracket around it and write down 2 minus, because we want to show that we actually got the two electrons from the outside. So this would be the answer for this problem. Alright, this might be confusing a little bit, but if we have not learned it, just skip that then. Alright, next, CH3OH. So I'm going to draw C, carbon, as the overall central atom, and then draw 4 valence electron. Now remember, for H3, I'm going to put H3 here. Alright, so I'm going to put that and connect them. Now we have OH, or hydroxide. So if we learned it from the previous unit, hydroxide is OH minus. So if it's OH minus, what we're going to do is I'm going to put a hydrogen here, which gives you 6 valence electron, and then I'm going to put a hydrogen next to the oxygen, right? That connects together with the lone electrons. Alright, so this is it. So this actually fulfills the octet rule and also gives you a hydroxide that is being connected with carbon. So this is the actual figure of the Lewis dot structure of CH3OH. Alright, if it's confusing, just feel free to ask on the comments or during class. NO3 minus. So N has 5 valence electron, and then O has 6 valence electrons. Okay, so remember this is same. It's kind of similar as the previous question with SO4 2 minus, because there's a charge right here, extra charge. Same goes with here. There's an extra minus charge, which means there's going to be one more electron being added in here. So what I'm going to do is first connect the single lone electrons. And next what I'm going to do is I am going to, I'm going to add a random electron here. So that means this fulfills the octet rule. Alright. Next is this lone electrons. In this case, what we have to do is we have to connect the rest of the electrons that are provided in the nitrogen here. Because we don't want to leave a single electron just left over here. So fortunately, we have to break this apart and let them connect it with the electron. So if I redraw this out, there's going to be a double bond oxygen here, double bond oxygen here, and a single bond oxygen here. So overall, this is the right structure. And remember to put a bracket with a minus charge, saying that you took an electron, one electron from the outside. So this is the right structure because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, this is an exception as well. Having more than one electron, not having more than 8 electron actually. So this is the drawing for that. Alright, we have 2 more to go. So ClO2 minus. So I'm going to put Cl first because that is the central atom. Alright. So we have that, and then I'm going to put an O on both sides. So O has 6 valence electron in each. And remember, for this problem, what we have to first do is I'm going to put 1 electron in first. Alright, so 1 electron would go in. So I'm going to put it randomly here. Alright, connect those lone electrons. For this case, I'm going to take out the electrons from these pairs. I have no other choice. So this gives you a alright, remember to put a bracket and a minus charge. So this is your answer for this problem. Alright, this might be a little bit confusing because we haven't learned it, but no worries. You'll get to learn it or understand it as you go on. Lastly, CH2O. So carbon is the central atom, so I'm going to put four valence electrons and put a hydrogen on two sides. Now remember this, we actually had this problem on the previous page, but I'll just go over it. So there's going to be oxygen here with 6 valence electron. Alright, remember to connect the lone electrons together, and that will create this structure. Alright, so this is basically it. If there are any questions regarding to any of these compounds, feel free to shout out the questions that you have onto the comments or in class. So if you have any questions, feel free to ask, and I would gladly and happily be able to answer your questions. So yeah, that is it for the Lewis dot structure, and hope you guys like the lectures that you have done today.